Okay, welcome to the afternoon. I hope you all enjoyed your time outside. So now we get to spend more time inside. So my name's Sam Tobin-Hochstadt. I'm at Indiana University when I'm not coming to visit you all. And I'm going to be talking over the next few days about two big and interrelated topics, about contracts and about gradual types. And today we're going to focus mostly on seeing some examples, seeing some questions that we might want to answer about these topics, figuring out what they're for and why we might care, what we can do with these things. And then in the subsequent lectures, we're going to look at the semantics. We're going to follow the program that David talked about this morning to try to understand more deeply exactly what's going on and figure out both how we can answer some interesting questions and also how to prove some interesting results about systems with contracts, systems with gradual types, so that we know that we're working with what we hope to be working with. Feel free to ask lots of questions, of course. This is going to be, today, pretty much focused on code examples, like in Edwin's talk, looking at some small programs, seeing what we can write, and what we can end up with when we do that. So. To start with, here's my favorite text editor in which I'm going to be writing programs. This is Dr. Racket. This is an IDE designed for writing Racket programs and anything else that you can pretend to be a Racket program.
Yeah, sorry, should we follow along with that way?
You're welcome to follow along. You're also welcome to just listen and then get the rewatch the video or get the code afterwards. I'll try to post it on Piazza, so any of those things is fine. But you're welcome to follow along. I see that there's a few people who at least have Dr. Racket stickers, so maybe that means you also have Dr. Racket. If not, it's pretty easy to install and download, and that'll be useful when David uses some other cool things that come with Dr. Racket tomorrow, probably. But to start with, here's just a simple program written in Racket, and one of the things to know about Racket is that it has a lot of parentheses. So that's the most important thing about any programming language is how many parentheses it has. Racket's sort of in the middle. It has more parentheses than Haskell, but fewer than JavaScript. So what contracts and gradual types are really about is about specification. So to talk about specification, all we mean is some way of describing what it is that we want our programs to do. And we're going to start with a function that has a sort of interesting specification, which is the Argmax function. So Argmax takes a function and a list and figures out which element of the list maximizes the value of the function. So this is pretty simple program. But let's start not by writing down the function that we want, but thinking about what its specification is. And we'll look at a few different options for specification. So I'm going to start by writing the specification just as a comment. That's what these tan things are. I'm going to mirror my screen also so I can see what I'm typing. There we go. So here we go. Argmax. And the specification for Argmax, we just said it takes a function and a list, and it produces a thing. So this is this is a bad specification. You can tell by the use of the word thing, also the use of the word function, and those are usually words that do not appear in useful specifications for things. We want to say more about this. The way that I teach my first-year students to specify something like Argmax would look something like this. So this is the kind of specification that presumably many of you will recall from yesterday or the day before when we talked about polymorphism in programming languages. So we've given this a polymorphic specification that's quantified over what sorts of things might be in a list. And we can give this function a much more detailed specification, though. This is still a pretty loose specification. What other things might we want to say in the specification? What other things are important in the specification for the Argmax function? Yeah? So other things that might be missing from the specification.
The list must not be empty.
Yeah, that's a really important point, because if the list is empty, it's very hard to produce an A. So this is actually a deep result in programming languages, is that this program does not produce an A if you give it an empty list. This is something that you can get this is something you can conclude just from this type by means of what's known as parametricity, that if you give it an empty list, the program will error or diverge. We can guarantee that. So therefore, since we don't want that, we want to have a precondition that the list is not going to be empty. Yeah?
The return value should be within the list.
Yeah, so other things.
Well, the return value should be. Are we coming up with? Sorry. Oh. Are we coming up with the value of the function, the placeholder, or the initial value? I guess there are three things we might return. Oh, we're return.
I think there's only
we're
one.
Just returning the end. No, I'm sorry.
Yeah.
I'm good.
We need to only accept hex A that have some comparison operation on it.
So that's not quite right, but there's an important caveat in the neighborhood of that, which is we said this function produces numbers, right? And the numbers need to be comparable. So that's a really important point. Now, of course, all numbers are comparable, right? How could it be that there are numbers that are incomparable? So we've had two different disturbing suggestions for numbers that might be violating my expectations that all numbers are totally ordered, which is that, so we need to say the numbers must be comparable. And as people have pointed out, there's trickiness when you try to compare floating point numbers, because floating point numbers are terrible. There's also trickiness when you try to compare complex numbers, because there's not a default ordering on complex numbers. There's, in fact, a wide variety of orderings on complex numbers that you could choose from. Yeah?
Don't you need to decide what happens if like two values evaluate the same value?
Yeah, what if, which value should we produce if two elements, if our function produces the same thing for two elements? What should we produce? So it definitely, so let's, when would it matter? So you might say, well, it doesn't matter. We said they're the same, but when is that not going to?
There might not be like a unique mapping from numbers to X to A.
Yeah. So what would be a function where this would come into play? Yeah?
Length of a list.
Yeah, so length of a list. What's an even more extreme example? Yeah, a constant function. What if the function we provide to argmax is lambda x dot 1? Now that's going to be, it's going to be hard to figure out which element produces the unique maximum value from lambda x dot 1. So we have to figure out which answer we want. So that's another thing. What should we pick? What answer should we give if we get two numbers that are the same? Yeah, the first one. I like the first one. Okay, other things that we want to specify.
The function is total on the input.
That is a really interesting point. So the function should be total on the input. Okay. So for example, if we have the log function as our function, and we have a list of numbers, if some of those numbers are negative, then we might be sad. Well, actually, we won't be sad in Racket because Racket defines the log function on the negative numbers, but you get the idea. If we have a function that takes the first element of the list and compares that, and we have some empty lists, that's going to be a problem. If we have a function that diverges sometimes, that's maybe also going to be a problem. So we've got a lot of possibilities for ways in which the function could go wrong. So while we're thinking about that, there's more things that we could say with respect to totality. In particular, there's one special case where it's okay if this is not correct. If that condition is not met. What's that special case? Yeah.
When the list is empty.
So the list can't possibly be empty. We definitely said that is right out. But close. when the list is almost empty, but if it has one element, what is the maximizing element if there's only one element? It's that one. That was easy. We didn't need to know what the function was. We didn't need to know what the value was. We didn't, in fact, need to call the function at all. So, yeah?
Are we allowed to do that? Like, you might write a program that depends on the function.
We might indeed. This is the wonderful part of what we are doing right now, which is, in the grand tradition of computer science, we are making up what we are allowed to do and then doing it. That's the thing that makes this discipline so much fun. But more seriously, we are choosing the specification. And we might say our Argmax will call the function exactly one time on every element of the list. We might say it'll call it at least once on every element of the list. We might say we'll call it at most once on every element of the list. We might say we'll call it exactly once on every element of the list unless the list has only one element, in which case we will not call it ever. We might specify what order we call it on the various elements of the list. All of those things are possible, and we can think about writing those down in the specification, and we'll try writing down contracts that implement various aspects of that, those specifications. So but let's just say that for our specification, we're not supposed to call it twice. That is, we shouldn't call the function unnecessarily. Yeah. Well, so we're going to assume a sequential programming language, and therefore, if you call it 3 times, you necessarily must have first called it twice. Yeah. So, but that's a really good question. Is when do we check these specifications? When do we decide if we've satisfied our specification? Is it at the end when our Argmax function is done? Is it at every instant during execution? Because those are 2 really different things. And you might say, because, so let's add another specification element that really brings that to light, which is the function is not supposed to change the file system. Yeah? Okay, anyone else want to complain about this specification? Yeah. So we could say that that's a much stronger than must not change the file system condition.
What if the function a to number changes the file system? Are we saying that we are allowed to and it may, or that
so by the function here, I mean the argument. So maybe we'll give some names to this. Call that F and L. So F is not supposed to change the file system. But that's another really good point, is who's not supposed to change the file system? Is this an obligation on Argmax, or is this an obligation on the clients of Argmax? And so there's a variety. So now if we think about this, we get back to your point about when are we checking? Because what does it mean for F not to change the file system? That's a question that really depends on what we mean by checking that. Because imagine it creates a temporary file and then deletes it. Does that change the file system? Maybe, maybe not. depends whether we're checking before and after we call f, if the file system is the same. Yeah.
Depending on how pure our functions are, we might want to enforce that the list doesn't have any duplicate elements.
Yeah, so we might, that's certainly a possible specification. We could say there's a variety of things we could say about duplicate elements, actually. One thing is we could say the list shouldn't have any duplicate elements. Another thing we could say is if the list does have duplicate elements, we're only going to call the function on one of those duplicate elements. Plus, there's an interesting question about what do we mean by duplicate elements? We've got arbitrary a's here. When are two a's duplicates of each other? We could say they're duplicates if Racket says true to EQ with them. That's pointer equality. We could say we need to be provided with an equality predicate. We could say use a different function that Racket provides for comparing elements. There's a variety of kinds of duplicate checking that we could have, but I want to make Argmax work even if there are duplicate elements, and we'll just ignore those complications. So we might say the function should not change the file system. Another interesting, but I think actually that's too strong. We might want to have this work for functions that we might want to figure out which file name has the largest size. And it turns out that getting the size changes the A time of your files because it does. But you could say something more sophisticated like Argmax does not change the file system any more than f. So this is saying that if f does some changes to the file system, that's your problem. You're the one who wrote f. But I'm not going to do anything more than you did when you provided me with f. And now we see one of the reasons why it'd be really important to say something about how often we're going to call f, how many times we're going to call f, in what order we're going to call f. So all those can be really important. Any other ideas for things we could put in the specification for Argmax? Okay. So now I want to, yeah.
Oh, wait. Where is the type variable quantified?
Does
that have to be capable of taking any A and returning a number?
So let's answer that question by writing Argmax in typed Racket. So here, I'm going to so here's a definition of Argmax, which answers your scoping question, or at least a type annotation for Argmax. And we might want to, and now we'll write it. And this is written in typed Racket. One of the fun things about Racket is that you can change which programming language you're using by changing the line at the top of the file. And so here's, we've done a couple things in this specification. We've said, we've taken care of the numbers have to be comparable because the reals are totally ordered. I can say that since Frank left the room. And we've specified that the input has to be non-empty, because we've defined this type non-empty list of, which is a pair of an A and a list of A. So there's bound to be at least one A there. So now we have to write Argmax. And Argmax is pretty easy to write. So there's Argmax. And for those of you who are not Racketeers, we'll walk through what this code does. So the basic idea is that we're going to go through this list, which, remember, we know to be non-empty. We know that from our specification. And we're going to keep track of three things. One, the biggest value that we've gotten out of F so far. Two, the element of the list that produced that big value. And three, the remainder of the list that we have to process. And when we get to the end of the list, we're going to return whatever element produced the biggest value, and that's Argmax. As long as we've maintained the invariant that we've always got our hands on the biggest value and the biggest output. So we're going to start off with FV being the biggest F, or the biggest output that we've seen so far, which is, of course, just whichever the first output we see is, that is F of the first element of L. Now, what value produced that supremely large value? Well, it's whatever the first element of L is. So FV is the biggest output we've seen, and V is the input that produced that biggest output. And L is just the list that we have remaining to process. And we've already taken care of the first element, so we've just got the rest of it. And then there's three possibilities remaining. One, we're done. There's no more elements, so V is the biggest thing we wanted to produce. Two, we've got some elements, and this is a new big element. F of this element is even bigger than FV, the biggest one we've seen so far. Now, in that case, we're going to forget about the old FV, we're going to forget about the old V, and we're going to remember the new thing we've got and continue processing the remainder. If it wasn't bigger, well, who cares about the element we're looking at? We're going to forget about it, continue with the things we were remembering before, and continue on our merry way. So far, so good. So this is Argmax. Yeah? this violates our specification in all kinds of ways. So that is an important one. But first, let's think about which parts of our specification this does and doesn't uphold. So we did successfully write down that the list shouldn't be empty. And in fact, we get a type error right there when we try to call it. We also successfully wrote down that we have to be using numbers that we can compare. So this is also a type error because you can't compare the complex numbers. Of course, sadly, we've made the unfortunate decision to make IEEE floating point numbers comparable, so this program type checks just fine. But computers are annoying sometimes. So we've taken care of a couple elements of the specification. Yeah?
Will it fail to compile with the empty list only if it statically knows it's not empty, or will it, like it can't statically determine if the list is empty, will it always compile or always fail to compile?
It will always, this type says has to be non-empty, so so let's try that. Yeah, that's a type error because and that's still a type error, even though if I hit run a bunch of times, probably, well, this is the one that's unlikely to trigger, but still a type error. Okay, so now let's think about which parts of the specification we do satisfy and don't satisfy. So we checked that the list must not be empty. Turns out that the type itself guarantees, like I said, because of parametricity, that the returned value is in the list. Because there's just no way for it to not be in the list. The numbers are comparable, like we said, because the reals are totally ordered, or so we pretend. We had to write down real here to tell the system that we wanted things that we could compare. If I just wrote number here, we get a type error. So we've gotten some parts of this, but we've missed a number of parts of this specification. And those are parts of the specification that much harder to write down with the type system, and so we're going to turn to look at contracts for them.
Yeah, so about the non-empty list type, you say it's a pair of A together with a list of A?
Yes.
But when you just pass it a list and it type checks, how does that work?
That's because lists are made up of pairs. And in classic Lisp tradition, lists are just a recursive type defined over pairs. And so a pair of an element and a list is a list.
And how does then type Racket not run into the problem of like recursive pairs?
Very carefully. So fortunately, smarter people than me came up with clever algorithms for doing things like subtyping and equivalence checking on arbitrary recursive types, and typed Racket does that. Yeah?
I was wondering, in typed Racket, is it possible to dynamically check the type in the function and do something differently based off?
Yes, it is.
Seems like we wouldn't be satisfying the return values in the list. Because we say if it's an integer, always return a million.
The reason why that's the case, so you can, in typed Racket, write programs that check whether something is of a particular type and do something different based on that. But we can't check whether something is an A. We don't have any, just like we don't have a general way of comparing A's in a particular way. We don't have a way of testing for A's. So we can be sure that we're always going to get elements out of it.
Though, right? If you ask if it's an integer and then return 5.
No, that will not type check.
So you can't check at runtime. There's no representation of A.
Right. There's no representation of A, and the reason why David's suggestion doesn't work is we could check whether one of the elements was an integer. That's perfectly easy to do. What we can't check is whether integer is the same as A, which is what we needed. We can't check some element of the list and thereby learn something about the A that was the case for the whole list. We can learn that if you have 5 in the list, then the type that contains only 5 has to be a subtype of the type that we're using for A. But that's not enough to go the other way and say the type that we were using for A also contains a million, or we get one direction of implication, but you can't just go from one direction of implication to the other direction of implication. Otherwise, all my math classes would have been much easier.
So does that mean it's possible to refine data types to restrict it to like some subset?
Yes, it is. So there's lots of people in this room who have done lots of cool things with refined types. I think it's unfortunately not going to be something we have time to talk about this week in lecture, but if you want to talk about it more offline, we can do that. Yeah?
So I think there's a restriction that we want to have on the definition of Argmax, which is it shouldn't violate parametricity. So we shouldn't, like, even if we can't tell whether A is integer, we still shouldn't be checking the types of things at all. Like, we should be treating them as opaque.
Yeah, so here's a interesting version of Argmax. Interesting. Yeah, so that seems like not what we wanted. And yeah, and typed Racket does in fact allow you to do that. The parametricity guarantee here is limited. It's enough to be sure that we're getting out elements of the original list, but it's not enough to ensure that the behavior is genuinely parametric. So we're doing two things. We're checking that Argmax lives up to this specification, and we're checking that the client of Argmax, that is line 25 here, lives up to this specification. Key thing about specifications is that they're an agreement between two people, and we're checking it on both of them. So yeah, there's two different checks. Okay, so that's enough about type checking. Now I want to start looking at with contracts. So here's Argmax again. I'll take out this bit. And now I want to start thinking about writing down some of those specifications in the form of contracts. And I'm going to write that using Racket's contract system, which is going to look like this. So this goes back to our first specification that I said was bad. Takes a function and a list, produces a thing. And that's what we've said here. That we've got this notation is a contract, and it's a function contract. That's why we write it with an arrow. And our function has two arguments. And then the thing that's distinctive about contracts is that unlike types, or maybe like types if you're Edwin, contracts are written in the same language that we write the rest of our program in. So procedure question mark is just a regular old Racket function that answers true for procedures and false for numbers and strings and lists and input ports and that sort of thing. And list question mark is similar, and NEC is a contract that always succeeds. So just saying returns something. So we've now satisfied the most trivial specification, and when we run this program, it does in fact do that. And I'm going to write our first contract error. And okay. So here's a program that works correctly. We can call Argmax on this list, and we successfully get 3. And if we pass it something that doesn't satisfy the contract, we get an error. And so one of the really important parts about contracts is the errors that they produce. So I want to talk a little bit about this error. So there's a few different parts of this error, but the most important one is this line right here, which is about who gets blamed. Remember I said a few minutes ago that specifications are all about agreements between people. So, for example, they invited me to come talk to you, and they made the agreement that they would provide me with this delicious iced coffee in return for this lecture. Thanks, Zaina. And if we had failed to procure the iced coffee, then there would have been an error, a failure of that specification. And it's really important to figure out who's at fault when a specification goes wrong so that you can figure out how to fix your system and make sure that no one ever is without their coffee again. And that's what contracts are all about. Contracts tell you who broke the specification. And that's what this line says right here. It says that the test submodule, that is this part of the code right here, broke the contract. Where did the contract come from? It came from this file. And here's what the contract was. Here's what the value was. Here's what we expected to see, which is a list. Here's what we actually saw. And it was in this contract. So that's a contract error. And we can now start looking at more interesting programs and more interesting, in particular, more interesting contracts. So let's write, but one thing that I want to really emphasize is that this is a dynamic error. This is a dynamic check. If we hadn't run this code, then we would not have seen this error. This is not like a type system where in order to run the program, you first have to check that nothing bad will ever happen from the perspective of the type system. Instead, we're just going to track it at runtime. So now let's make our contract a little more interesting. So now we've got a contract that looks somewhat like what we had for our type in typed Racket. That we've got specification on the function, which says that it's going to produce real numbers. We've got a specification on the list, which says that it's non-empty, and we can check this. So, and this one passes. And let's see. So there we have an interesting program. So what's interesting about this example? Does this example satisfy our specifications?
Square root's not total.
Square root's not total. Well, what if, so square root is, it turns out, as we just saw, total certainly on this list, but square root does not always produce real numbers. This is not a real number. So what's going on here? What's interesting about this combination of program and specification? Yeah.
Parts of it are kind of wrong, but the whole thing is correct, if that makes sense?
Yeah, that's actually a really nice way of putting it. So one way you can think about this is that whether a contract is satisfied is not a property that you can determine just by looking at the value, the thing that you're applying the contract to. You also have to look at the context in which it's being used. And this, of course, you can look at the contract as a more general specification mechanism, in which case square root does not satisfy this contract. But in this program, the whole thing that I have on my screen does not produce any contract errors. So this is a way in which contracts are quite different than some other ways of doing specification, such as types. We're going to allow this program to work. We're going to allow this program to succeed, even though in other contexts, square root does not meet this specification. In fact, square root really doesn't meet the specification that I've highlighted. What are some other ways in which square root is going to not be a good fit for the specification I've written here? Yeah. So if fortunately square root in Racket always produces one answer, so we don't have to worry about that. But if we did have something that was non-deterministic, then we might be in trouble. What's another way in which this specification is a little problematic for square root? What's the domain of square root? Real numbers, yeah. What did we suggest the domain of this function was? Anything at all. But the set of anything at all is bigger than the set of real numbers. And therefore, we've put a much too weak specification on this. It turns out that there's some subtle dependency between the use of the function and the list we pass in, and so we're not actually going to run into this problem. But this is not a specification that square root satisfies. It does not promise to return you real numbers given arbitrary inputs. So contracts as a specification discipline are characterized by a few things. One, they're programs written in the same programming language that you've already got. Two, they are a fundamentally optimistic sort of specification approach, where you try it, you see if it works, and if it happens to work this time, then you say OK. You do not attempt to verify that something will work universally before proceeding. And in fact, at runtime, testing whether square root actually lives up to this specification would be difficult. We've got arbitrary computational power here, checking arbitrary functions against their specifications before running them is a difficult problem on which many people have spent their time. But the nice thing about contracts is we just ignore that problem and instead focus on the simpler problem of not checking things until we really, really have to. And so the way that this function contract works is we don't check anything now. We just wait until square root produces some answers. And each time it produces an answer, we check whether it's actually a real number. Yeah?
If we endow the wrapper
So Racket has a few optimizations for eliding particular redundant contract checks, but in most cases it's not going to be able to get that one. So one thing so I think what you're suggesting is, what if we did this? So now we know that f of z is going to produce a real number. Otherwise, we're going to get an error blaming f. So let's actually look at what that error looks like. So here's f. We see that f is the one that's broken the contract, and we're blaming the test module, and we've gotten, so unlike previously where we blamed the client, the person using Argmax, now we're blaming the definition of f, because the definition of f said, if you give me anything, I'll give you a real number, and that's manifestly not true. So we can strengthen the contract for f. Of course, that's not quite strong enough. We need contract like this. And so f promises that if you give it a value that's at least 0, it'll give you a real. And so now we're blaming this submodule. Call this main, just to be clear. Now we're blaming main because main is the one that passed f into a context where f was misused. So the important thing to think about with contracts is who's responsible at each point in time for living up to which parts of the obligations. And you've got to always keep track of who's promised to do what. So let's look at these two contracts. We've got f, and what f promises is that if you give me non-negative numbers, I'll give you real numbers. Now, we're a client of f, so when we import f, we are promising to live up to that contract. Then we hand f off to someone else. Now, that someone else did not make a strong promise to us about what they would do with f. What they promised was they would hand anything to f. They made no promises about what they would do to f. But we gave them access to f anyway. So therefore, the misuse of f is our fault. Friend of mine liked the following analogy for understanding blame in a higher order context. Imagine that you have a trash compactor and you'd like to borrow my car. And I say, Now, I could say, well, I'm willing to loan you my car as long as you take care of it. And in return, here's something you can put in your trash compactor. But you have to give me something first. And then we'll put that in your trash compactor. So I loan you the car, and then you give me this big gift-wrapped thing. Then we put it in the trash compactor and crunch. Now, who's at fault when it turns out that the thing in the gift wrapping was my car? Now, it's all about what did you promise to do with the car, and what did I promise to do with the thing that's going in the trash compactor? Now, if I didn't say anything about my promises, if we made no promises about the trash compactor, but strong promises about the car, then it's you that's at fault, even though I'm putting my car in the trash compactor. Because you promised to take care of my car. I did not relieve you of that obligation, so therefore, this is your fault. And that's what's going on here. I have promised to take care of F. Then I've handed F over to Argmax, which does not promise to take care of F. And then F becomes unhappy about its input. That's my fault, because I did not defend myself by expecting a high standard of behavior from Argmax. So we can push our contracts further onto other people by taking this contract and putting it here. And now Argmax is blamed because it promised not to call the input, not to call the function with anything less than 0, but it did. So Argmax is going to need to have a stronger contract on the list of numbers. So now we'll add another contract which says that our list of numbers has to all be positive. So now Argmax defends itself more. And now it's back to the main module's fault again for passing this list of numbers that isn't all positive. So we can push the blame around here by each person that gets blamed adds a stronger contract that ensures that it's not their fault. Then blame goes to somebody else. Then they say, oh, well, I didn't want to be blamed for this software failure. I'm going to write down a stronger contract. And now blame is going to go to the next person in line. And this is a hopefully virtuous cycle that ends up with everyone writing nice, strong specifications describing what they want. But now let's try to write a little more interesting specification. Try to capture a little bit more of the behavior that we wanted. So here's Argmax again. And all we've said is that we've got a non-empty list and a function that produces reals. Now there's a number of things that we could say about this specification. But in order to say them, we're going to need to go to a stronger form of contract. Yeah?
How does this contract state that the list is not empty?
So if a list is a pair, then it's by definition not nil, and therefore it's an empty list. It's not an empty list.
Okay, but then why not just say it must be a pair?
Because not all pairs are lists,
But all lists are pairs.
except the empty list.
Okay, so if something is a list and a pair at the same time.
then it's definitely a list, and it's not the empty list since empty lists aren't pairs. So therefore, it's a non-empty list. And that's exactly what we're saying here. We could also say that's the same thing. But the implementation of this is the same as the code that I just deleted and replaced with this. So these are the same. Okay. So let's write a stronger contract. So to write a stronger contract, I'm going to have to change this function contract into what's called a dependent contract. Should be familiar from Edwin's talk earlier and from discussion of dependent types earlier. We're going to be able to refer to the values of our inputs in the contracts. So here's the same contract written as a dependent contract. Dependent contracts are written with arrow I for reasons that we'll talk about in a subsequent lecture. But so far we haven't said anything new at all. And this does exactly the same thing. But now we can start describing this result here with more interesting contracts. And I'm just going to so what this says is that R is found in the list L. It's a member of the list. I'll just write member. R is a member of the list L. So now we've expressed one of the trickier parts of our original specification by checking that we actually got back an element of our input list.
Were the things we were using before not predicates that took in a value and then return, whether it's, like for example, a real debt, is that not?
That is also a predicate.
So I guess I don't understand how this is different than that.
So what's different is we can now use L here to compute what the predicate is going to be. So previously, we could say things like real question mark or list question mark or anything or various some function contract. But now we have a dependence between the actual value that we get in and the predicate that we use to check the value that we get out. And that's a dependent contract. Yeah? So quick check is an approach to writing down properties, the specification in terms of properties that something should satisfy, and then randomly generating terms and seeing if the property holds. Contracts are a different sort of way of writing down specifications. You can write down properties inside contracts. So here we've written down you could write this as a property, and then you could, so one fun thing to do is, let's see if this works. So this ran a bunch of, called Argmax, with a bunch of random inputs that satisfy the contract, and see if we ever get any failures. So this is sort of like quick check for the specific property doesn't fail the contract. doesn't fail its own contract. And since we've expressed an interesting contract here, an interesting property, we're getting some of the benefit there. But really, these are, quick check is a testing approach. And this is a dynamic enforcement of specifications approach. So they're pretty different. More questions? Yeah?
What kind of runtime overhead does this contract need?
So arbitrarily slowly. Think about, but so that's on the one hand funny, but on the other hand it's sort of obvious. This is just an arbitrary program. Like, that's going to take a long time. We can do whatever we want here. There's some overhead for the actual infrastructure here, but most of the overhead is that we're doing some non-trivial computation. So, for example, this member check is going to have to look through, potentially through the whole list to check that it's actually there. So we've got potentially another linear overhead. We could make this much more complicated and much more expensive. So you can do whatever you want, and thus you can make the overhead as big as you want. Yeah?
Does this mean that you get contract violations inside contract specifications?
That is a great question. So let's think about when that might happen. When would we get a contract violation inside a contract specification? When could that happen?
We're checking whether something's bigger than something else and we handed a complex number. We're using a contract full version of.
Yeah, so when might that happen for this example? What might happen when in this example? What if we called f and it produced the wrong kind of answer? It produced a complex number. Then where are we in, who's agreed to that contract at that point when we're inside the contract? And that's going to happen if we call f in this specification. And when would we do that? We do that if we want to check that the result we got is actually maximizing f over all of the elements. So let's write that contract. So we can compute f on R, and this should be the biggest. We can compute f on all the elements. And then we want to check that so if we take the maximum of f applied to all of the elements, it should be no bigger than f applied to the result, right? This is a simple check for the actual functional specification of Argmax. But now we're calling f in a lot of places. Who's responsible for those calls to f? What happens when those calls to f go wrong? Let's take out the contract. So here, this program satisfies our contract because we've written Argmax correctly. But let's think about what happens when let's imagine we take the argmax of square root list 1, 2, 3. That'll be fine. How about the argmax list -1? So this will produce an error. We expected to get a real number, but we got I. However, if we remember earlier, we said when there's only one element in the list, we don't really need to call the function. So let's change argmax to do that. Now argmax doesn't call the function if there's only one element. So this program should successfully return -1. But what's going to happen? What's going to happen is we get an error here saying we applied max to the wrong, we got an error. We tried to take the max of an imaginary number. That doesn't even make sense. Note that in order to do that, we've already called f on L. But so we have an interesting question. What should happen when we call f, which, as you see, has this specification, supposed to produce real numbers, on -1 from inside the contract? And whose fault is that? Is that the fault of the program that defined argmax? Is that the fault of the program that used argmax? Is that the fault of the person that wrote the contract? Something else? No one? Everyone?
So I'm kind of confused why it even type checked this isn't where we used it in a place where we said a function has to return the real, right? In the original type signature.
So if we had a type checker here, then no, so there's no types in this program at all. Yeah, if we switched back to being in typed Racket, we would get type errors saying that comparison requires real numbers. So this is an interesting, tricky puzzle. We've seen some other interesting questions, and what we're going to do next time is talk about how to formalize the semantics of contracts, how to state these questions in a formal way, look at some different possible semantics, and come up with some criteria that will let us distinguish different semantics and decide what the criteria are for a good contract system and whether this is the right answer. So that's it for today. So I guess we have a 10-minute break.